item of the recap is equiprobable sample spaces. Okay, so we learned about equiprobable sample spaces, and what is an equiprobable sample space? Well, usually I don't tell you nothing, and that's usually an equiprobable sample space. If I tell you that I'm tossing a coin and I don't give you any other information, it is that the fact that that coin is a normal coin, and the heads or tails have the same probability of happening. So this is considered an equiprobable sample space. The outcomes have the same probability of happening. Okay? Now, if I give you an information that the environment or whatever, your coin or your deck of cards is biased or unfair, or that something has the double of the probability of another thing happening, that's not an equiprobable sample space. Okay? And actually, we only know how to calculate probabilities inside equiprobable sample spaces, right? Like, at least for this course. So when we are inside an equiprobable sample space, sometimes you will be asked to calculate the probability. Up until now, we saw the properties of probability. We saw equations that relates probabilities. We saw formulas, but every probability was given to us, and then we had to find something, right? Now, inside these equiprobable sample spaces, usually you will be asked to calculate the probability. And the concept that we learn to calculate a probability inside an equiprobable sample space is this. What's the probability of event E, whatever event E is? Well, it's a ratio between the number of outcomes of interest, or like on event E. So it's the number of outcomes that interests me, right? So in this case, the number of outcomes of that particular event E divided by the total number of outcomes, or the number of total outcomes of my experiment. Okay? So this is like the pizza thing. So what's the probability that, or the coin, right? So the coin, you have heads and tails. What's the probability of having tails? Well, it's one particular outcome, the outcome tail, that's my interest, over divided by 2, which is the number of the total number of outcomes that you can have, heads or tails. So you have within 2 possible outcomes, you have one that interests you. So the probability is 1 over 2. Or the pizza. What's the probability that you get a particular piece of pizza? Well, if you have 8 slices of pizza and just one interests you, the probability of getting that particular slice of pizza is 1 over 8. Okay, or one particular event of interest over the number of total possible outcomes, which is 8. Okay? So this is what we learned about equiprobable sample spaces, and that's how we calculate probability, how we will calculate probability here in this course. Another thing that kind of is a consequence of being inside an equiprobable sample space is how to calculate the conditional probability. So we remembered that the conditional probability is given by, well, if F happened first, so probability of E given F happened first, and then E happened next, you're interested in the probability of then both happening. Okay? That would be the natural path, but you have to normalize or just divide by what happened first, right? So we saw this formula already. Now, this formula is generic, but when you are inside an equiprobable sample space, you can actually simplify this And you can calculate this conditional by just having the number of outcomes of this event, that outcomes that kind of satisfies the intersection, over the number of outcomes of the event F. Okay? So it's a consequence. It's a consequence of being inside an equiprobable sample space. You don't need to use the first formula. You can use this one here. You can calculate the conditional by having two counting problems. In the numerator, you will have the number of outcomes that satisfies the intersection. And in the denominator, you will have the number of outcomes of what happened first. So it's just a counting problem. That's why, because of item 7, that's why we have to learn counting, right? We have to learn counting because in the end of the day, to calculate probability, it's just a ratio of two counting problems. Counting the number of outcomes of interest, right, divided by the total number of outcomes, or in this case of the conditional, the number of outcomes of interest, which is E inter F, divided by the total number of outcomes of what happened first. Okay? Now, this is kind of, it's too blah, blah, like it's too wordy. Let's do some exercises, okay, to kind of sink in the content. So here's the first exercise. It's a little bit small, but let me see if I can make it a little bit bigger. Okay. So here's it. Here's this exercise is from midterm 2 last term, 2024. Okay. So it says like this: a subset of a set ABC is selected at random. Okay. So let's say that you have a bucket with all the possible subsets of ABC. And you're selecting them at random, meaning you close your eyes, you just put your hand inside the bucket and you grab one. Okay? The question is this: what's the probability that the subset that you kind of got, the subset that you draw, contains exactly one element? Okay? So first of all, when you read this exercise, you're asked to calculate something. You're not giving probabilities. Kind of, you're not giving any probability to find another probability. You're just giving something that's happening, and we're asking you to calculate the probability. Meaning that when you're asked to calculate things, probably you are in an equiprobable sample space, because that's the only way we know how to calculate probabilities. But you can always check. Like if you have a set of ABC and you have all the possible subsets, and I didn't say anything, I'm not saying that there's a particular subset that has more chance of being drawn than the other. Okay, so it's every subset has the same chance of being drawn. Okay, I didn't say that it's unfair, that the system is biased or anything. So we are inside an equiprobable sample space. So again, is that you have a bucket, you have a bucket. Inside the bucket, you have all the subsets. So for example, you have A is a subset. You have A and B is another subset. You have ABC is itself another subset, and so on, right? You have several subsets in the bucket. You're going to draw a subset. And the question is, what is the probability that I draw, that my subset that I draw, so the subset that I draw contains exactly one element? This is the question. This is the event. Okay, so probability of this event happening. Well, if we have to calculate, the ratio is where we have to go, right? The ratio of the things that interest me divided by the total number of things, okay? So this probability here, the probability that the subset contains exactly one element will be given by a ratio of the number of subsets or outcomes, or the number of ways of interest. So what interests me? Well, it's the number of subsets that has exactly, subsets with exactly one element, divided by the total number of outcomes. So divided by the total number, the number of total subsets that I have. Okay? So you have a bucket. You will have a total number of subsets there, right? And you'll draw one. What's the probability of the one that you draw has a single element? So that's the ratio. I want the number of subsets. That's the number of events of my interest. So the number of subsets with one element divided by the total subsets. So now we will have to go back to midterm 1 and remember counting. So so let me copy this phrase. The probability that I want will be, let's see. What are, I usually tend to start on the denominator. What are the total number of subsets that I can, that are inside my bucket? Who remembers that? Yeah. 2 to the power of 3. Okay, so if you don't remember, if you don't know what I'm talking about, I'm going to do a very quick recap, but if you're not comfortable, I suggest you to go back a little bit and remember how we count the number of subsets of a set. But this is 2 to the power of 3, or 8, right? So 2 times 2 times 2 equals 8. Well, if you remember midterm 1, you always have to answer this when you're selecting subsets. You have to ask a question, either if the elements are in your set or are not in your set. And you will do that for all the elements. So you do that for A, then you do that for B, then you do that for C. Okay? So if you think about this path here, this is the null set or the empty set, right? This, for example, is the set of only A, right? So it's A and not B and not C in your set. So if you think about, you have, in total, you have 1, 2, 3, 4, 5, 6, 7, 8 different ways of subsets, 8 different subsets, which is the denominator, okay? So even if you don't remember the formula that it's 2 to the power of number of elements, you could go on the side and just catch a little tree and see how many subsets you have, okay? Now, what is my numerator? Well, how many of these subsets are of my interest? Well, they're actually, you can go through the paths, or it's so easy because it's only 3 elements. This is just, this set is of my interest, which is just only A. It has only 1 element. What else? B. What else? C. So I have three things that interest me. Okay, so what is the number of subsets with 1 element that interests me? Well, 3. Okay, over divided by the total number of possible subsets that I can do, which are 8. And that's the probability. So this is actually equal to 3/8, and this is the answer. Okay? So you will have, I would say that you will have some of these exercises that are kind of simple. I mean, you will have to remember midterm 1, that's for sure. But they're kind of simple because even if you don't remember that much, you could find the subsets of 3 elements kind of easily. This kinds of question is the ones that you cannot miss. Like if you leave the error to the the more complicated ones. This kinds of question, which is just the number of things of interest over the total number of things of interest, and it's easy to count. You can count by hand. This is the question that you cannot miss. Okay? All right, questions. Questions about this exercise. Good? All right. So this is one type of exercise. It's a multiple choice, so it's kind of the simple ones. All right, now what I'm going to do is I'm going to solve another exercise. Which continues to be on the recap of item 7, but it's a little bit more complicated. You will have to rely on your knowledge of midterm 1 and counting. But we will do it together, okay? So here's the exercise. The letters in the word babbling. I don't know if you can you read that? Like it's small, but yeah, okay. So the letters in the word babbling are arranged at random. Okay? So it means that let's say that you have your computer and you have babbling in the screen, and there's a button on the side named shuffle. So you click there, and the letters will rearrange randomly, right? So you would have like a possibility. You would have babbling, right? This is one arrangement, one possible way. Then you hit the button, and it could be, I don't know, A, B, L, I, B again, N, G, B, right? I don't know, something like that. This is another possibility. And you have a number of possibilities here, okay? So you will hit the shuffle button, and the question is this: what is the probability that all 3 B's are together? Okay? So again, you're reading the exercise. You're not giving any probability. You're asked to calculate a probability, right? Usually this will be in an equiprobable sample space. So you read again, see if there's any bias, any unfairness. No, meaning that the letters, like the probability of having this arrangement is equal to any other arrangement, right? So you don't have anything that's biased. So this is an equiprobable sample space, and you're asked to calculate a probability. All right, so what's the probability? The probability that you're asked is, what's the probability that when you hit shuffle, you have 3 B's together? So 3 B's together in your arrangement. Okay. Well, the only way we know how to calculate the probability in an equiprobable sample space is doing a ratio, right? So I have to calculate this ratio. The ratio, what's in the denominator? Well, the denominator is the number, the total number, or the number of total outcomes or arrangements of the word. So there are several ways that this word could be shuffled, right? So there are a number of ways that this word can be shuffled, and this number has a total number. So this is the number that has to be in your denominator. The number of total shufflings, let's say. How do you write this? Shufflings, like this? Okay? And what about the numerator? Well, the numerator are the number of outcomes of interest. So it's the number of ways, or the number of shufflings or arrangements that has 3 B's together. Okay? So amongst all all the total possible shufflings that you could have, right? There are some of them that are of your interest. So the probability of that happening is this number of things of your interest divided by the total number of things that can happen, the shuffles that can happen, okay? So now it's a counting problem. We go back to midterm 1. Okay. So usually I like to start with the denominator because the denominator is the total number of things. There is no restriction, and it's usually easier to calculate. So this probability here of 3 B's together, let's calculate first the denominator, the number of total shufflings. So how many letters we have in babbling? 1, 2, 3, 4, 5, 6, 7, 8 letters. Okay? Here's the question. How many shuffles, like how many permutations, different words I can do with this 8 letters? Almost. Almost. You're in the right direction. What happened? What should we be careful about with the word babbling?
Because we have 3 B's here?
Yes, we have 3 indistinguishable elements. And if you remember midterm 1, when you have indistinguishable elements, you have to correct for that, right? So you have 8 factorial, it's true, but because you have 3 repetitions of B, you have to correct by 3 factorial. Okay? Remember, every time indistinguishable things appear, you divide by the number of repetitions factorial. So what I'm talking about is this. If you were to count, right, by hand, like, consider that this B is B1, B2, and B3. They are not different, but I'm just consider that they have this label. When you shuffle again, if you count this, for example, now this is B2, they shifted places, right? If you count this as 2 different things, you're overcounting, because in the end of the day, it's the same word, all right? So you have to divide by the permutation the B's are doing within them. Okay, so this is just midterm 1. Okay, but that's the total number of things. The total number of permutations discounting this B permutation is 8 factorial over 3 factorial. Okay? All right. Now, so in the numerator, we need to calculate the number of these shufflings, of these arrangements that has 3 B's together. Well, if you remember, when we want to like fix letters together, and if you go to the recap for midterm 1, we did exactly one exercise like this. So what you're saying is that within this 8 letters, the cases that interest you are the ones that you stitch B's together, right? Think about this. Think as having 8 boxes, and imagine that I have alphabet letters here, right? Like kid alphabet letters. And what I'm doing is I kind of glue the 3 boxes together, and I'll throw the B's inside this box so that I'm guaranteeing that they're not being separated. Okay? And so I throw B there, and I can have other letters in the other boxes, right? So I can have L, I, N, G, and what else? What am I missing? L, I, A. Okay? Now, say that I have these boxes. Now, this is one way. This is one way of having 3 B's together. How many ways, total way, what is the number of ways that I can have this 3 B's together? What should I do with the boxes to calculate this? I should permutate them, right? Because this is one way, but this mega box, this mega slot here, can actually come after L, sorry. Right? And and all these letters, they can kind of shuffle, but you're gluing the mega slot together. So in the end of the day, you have these 8 slots are actually where's my mouse? It's 1 slot, 1 mega slot, 2, 3, 4, 5, 6 slots that are permutating, right? So 1 mega slot, 2, 3, 4, 5, 6, and you just permutate these slots. So it's the number of shufflings that has 3 B's together is 6 factorial. Okay? So I've said this in the other section. It is very important, and this is a tip, like you don't need to go back and study all the material for midterm 1, but it would be very, very, very helpful if you at least saw the recap videos for midterm 1. Okay? I think it's a 1 hour and 40 minutes, or I don't know, something of recaps. Just take a look at it before midterm 2. Kind of just refresh your memory on how to calculate this permutations and the indistinguishability and these things, so that you have it more fresh in your memory. Okay? Now, if I go to the multiple choices, like if I go to the A, B, C options here, I don't have this answer. Right? So, I mean, the answer is this one, right? It's C. How can we? Yeah. So actually, it is very common, and it depends on the year. So in every year there's some word arrangement probability to calculate. So it's very likely. I didn't see the test yet, but it's very likely that you have one question of this year. Now, in 2022, if I'm not wrong, or fall 2023, I'm not sure, the answer appeared like this, like I just described. In 2024, last year, it appeared like that. So, I mean, it will depend, and you will have to know how to go from one to the other and back, right? So what happens here? The answer appears as 8311111, okay? Actually, if you remember multinomial notation is this. 5. So multinomial notation is take the numerator and divide by the denominator's factorial. Okay? So this is the how we do multinomial notation. Obviously that 1 times 1 times 1 times 1 is just 1, and you're left with the same thing. So this answer here is just changing the notation for the denominator. Okay? So 8 factorial over 3 factorial is the same thing as 8 choose 3 1 1 1 1 1. Every time you see a factorial over another factorial, you can describe it with multinomial notation. That's a fact, right? You just take whatever you want on the top to be here, on the numerator to be here, and the thing that you want to the denominator being there. The rest you complete with ones, and that's the ratio between the two factorials. Okay? So it will depend. Sometimes you will see this answer like showing in a multinomial kind of style, or sometimes you will see in just the indistinguishable correction style. Okay, but there is also a way to interpret this problem differently. So this is the answer. This is the solution. This is the way I like to think about this shufflings of words. But you can also think this as a grouping exercise. So I'm going to solve it as a grouping as well, and you just pick your favorite. Okay? Well, as a grouping exercise, this is what happens. Imagine that you have the 8 boxes. 1, 2, 3, 4, 5, 6, 7, 8. You have 8 boxes. And what you're doing with these boxes is this. You're going to, from the 8, you're going to choose 3 to put letter B's on. And then you choose 1 to put the letter A, 1 you will choose to put the letter L, 1 letter I, 1 letter N, and 1 letter G. So what you're doing is a multinomial notation. You're choosing 3 from you have 8 buckets, 8 boxes. You're going to choose 3 of them, okay, to be B's. So you're doing this, 8 choosing 3 to be B's. Then the other one, you will choose 1 to be L, 1 to be I, 1 to be N, 1 to be G, and 1 to be, I don't know what letter is left. Well, it's 1 more. Okay? So, and why this works? Well, think about this. I'm choosing a slot to be L, but I don't care. Do you remember that the grouping mechanism is that you don't care where it happens? You don't care the position? It's exactly that. Like, I'm choosing one of them. Where? I don't care. Just give me the number of ways I can choose one of them to be L. Give me the number of ways of choosing 3 of them to be B, right? And that's what you're doing here. So it automatically comes with the multinomial notation if you think of the problem that way. It's up to you. It works either way. It's the same thing. Okay? You just have to just choose a train of thought. Just choose a way that you reason and go for it. But remember that sometimes the ratio of factorials can be written as multinomial notation. Okay? If you go through the last midterms, you will see that almost all of them has a arrangement of letters. And most, I didn't see the test yet, but most probably there will be arrangement of letters. So just work on all the ones that you can to practice. Okay? Questions? Yeah.
If you can't distinguish what the ones are, say you didn't know like what letters they were and this and that, like do you divide by 5? Is that what we did?
If you couldn't tell apart, yes.
Okay.
Yeah. Exactly. If you couldn't tell them apart, like but in the case of letters, there is a case that you have to correct for another repetition. There's an exercise from, I think it's 2023. It's the word raccoon. So you have 2 C's and 2 O's. So we incurred some other correction. I have the video for that. I'll be posting it as well. I have everything for you guys on. I'll upload that too. But it's the same reasoning, right? You will have to you will be left with another indistinguishability. You just correct again. Okay? Questions? Good? Yeah.
The raccoon one, so would you divide that by 2 times?
Yeah, exactly. Yeah, exactly. You got it. You got it. Exactly. Okay. We can do that. We can work out the raccoon as well. Like next Thursday, we will have another lecture. I can do the raccoon for you guys, just to kind of make it clear how it works. Okay. All right. So now I have yet another equiprobable sample space exercise for you guys. And again, it's a counting problem thing. I am not like you have to know counting, but it's like 1/3 of the test is this kinds of calculation with countings. The other 2/3, I would say, it's the properties of probability, like the equations, trees, and you're given probabilities and you're asked other stuff, right? 2/3, I would say that, but 1/3 of the test, you will have to know counting. Okay, so that's why it's very good to go back, at least for the recap videos, just to refresh. Okay, so here's the other exercise. This is midterm 2 2024. This is an open question, the open question of 2024. At a national conference, each of the 10 Canadian provinces has sent 3 delegates. If these 30 attendees, along with the Prime Minister, are randomly seated around a large circular table, what is the probability that all the 3 delegates from Ontario are sitting together side by side? Okay. So again, you're not giving any probability. You're asked to calculate a probability. It's an equiprobable sample space, meaning that the chances of one configuration is not higher than another configuration of sitting these guys, right? So let's go back and interpret this. You have 30 delegates, 10 provinces times 3, 30 delegates, and the Prime Minister. So you have 31 people to sit around a table. When you hear seat around something, right? If it's a circular thing, your brain should be like red flag on circular permutation, which is it's a content from midterm 1, okay? So what we have is, we have Ontario 1, the second delegate, third delegate, then we have, I don't know, Alberta 1, Alberta 2, Alberta 3, British Columbia 1, 2, and 3, and so on, and the Prime Minister. So you have 31 people, and you have to sit them around the table. Okay, so what's the question? The question is this. Amongst all the ways that you can sit these people, what's the probability that all 3 delegates from Ontario are sitting together, side by side? So what's the probability of having O1, O2, O3 together, side by side? This is our question. So what do we have to seek for calculating this? Well, what I have to do is to remember that probability is a ratio. Is a ratio of the number of situations that are of interest divided by the total number of outcomes. So the thing is this, amongst all the situations that I can sit these people, so the denominator is the total number, or the number of total ways, I don't know, that I can sit, 31 people. This is like all sitting arrangements, okay? And my interest is how many of these arrangements have O1. So how many? What is the number of ways or arrangements that have O1, O2, and O3 together? That's my question. That's what I have to try to answer. So it's just a ratio, and I have to calculate now for the denominator and calculate for the numerator. Okay? So what's happening here is, well, let's remember about circular permutation. It's not the same as linear permutation, which is the factorial. We had to correct for something. If you remember that, actually you have to take out 1, because somebody has to sit first. If you remember, it's what we call the internal reference. You can sit in a circle. You can shift this way or that way. You're still sitting in the same way. What counts is if you look to the left and that people is there, and if you look to the right, the people is there. That person is there. So you have to correct. In the end of the day, the waste is the total number together. The total number of ways that I can sit this 31 people is 31 minus 1 factorial. Okay, because circular permutations is like this. It's not 31 factorial. You have to kind of fix a first person to sit. It's 31 minus 1, so it's 30 factorial. Okay? Now, what are the number of ways? Now I'm left with the numerator. What's the number of ways O1, O2, O3 can sit together? Okay? So if you go back to the recap, we have an exercise for this. And what I can do is I can tell the Ontarians here to give their hands, or glue them together, right? So if you can imagine that I have 30 slots around the table, right? I have 30 slots. What I'm going to do is I'm going to say, okay, Ontarians, glue yourself together and sit somewhere, right? So if you think about this, if I glue 3 of the sits together, right? Like Ontario 1, Ontario 2, Ontario 3, they're glued together. How many slots that I will have to organize into a circle? Considering that the 3 slots here that were 3 slots, but they are now 1. They're a single slot. Right? So I had 31, right? But 3 becomes 1, so 29. I actually have 29 slots to sit around the table. Okay? So if you think about, I mean, I'm distributing this in a circular way. You can think about this. You have the first 3 slots are becoming 1. So before, this was slot 1, 2, 3, and 4, and so on, right? Obviously, they were being in a circular way. But now, like, number 4 becomes 1 slot, becomes number 2. So I'm losing 2 positions. I don't have 31, I have 29 to sit, okay? But should I sit 29? Is this 29 factorial? No, because I'm in a circular position. So this is actually 29 slots or people, kind of imagining that this 3 are 1 super people glued together. This is 29 minus 1 factorial. Okay? No.
Would you do anything like the 3 people like sitting beside each other, like
Exactly. So is this the answer? Well, you couldn't know because you don't have the multiple choice here, but it's not. Like, you're almost right. If you like do this, I will give you three quarters of the mark. You're almost there, but you missed something. What are you missing? Well, when I said Ontarios, can you give your hands or can you glue yourself together? Did I say that it had to be 01, 02, or 03 in this order? Well, it could have been 02, 01, 03. It could have been 03, 01, 02, 03, 02, 01, right? So how many ways that inside the super bucket of Ontarians, the super slot of Ontarians, how many ways they can shuffle, they can permutate? 3 factorial, right? So actually, the cases of interest is not just 28 factorial. It's actually 28 factorial times the modification that you can do inside the super slot. So times 3 factorial. Okay, and that's the answer. So the answer is 28 factorial over 3 factorial over 30 factorial. This is the answer of the exercise. And you don't need to, in open questions, you usually don't need to simplify, you just leave it this way, and that's a full mark for that. Okay? So at the end of the day, probability, when you're calculating it, not just using the properties, you're doing counting, right? You're doing two counting problems, the numerator and the denominator. Okay? Questions? Good? All right. So this is item 7 of the recap. And today I want to do the item 8 with you guys, and then we're done for today, and then we will continue Thursday. Item 8 of the recap is Bayes' theorem. Okay? So what's Bayes' theorem? Let's try to remember what Bayes' theorem is about, and then we will do an exercise. Okay, let me just give myself some space here. So Bayes' theorem is that horrible formula, like that we saw last, I think it was last lecture or the other one. It's a formula that flips the conditional probability. That's what Bayes is about. And you can obviously memorize the formula, you can, or you can do it on the fly. right? So I'm going to do on the fly, and I will kind of derive the formula with you guys. So usually what I do to remember how to derive Bayes' theorem is just using the sick, healthy problem, right? So you can be sick or you can be healthy. And then you can go and do a test. And you can return positive for the disease or negative. Okay? That's all you need kind of to derive the Bayes theorem. So what is the natural path, like the natural, because the tree is stochastic, so it means that it shows you the order of things. Well, you are sick or healthy, and then you do the test, right? So this is the kind of the sequence. So the direct conditional that it's natural for you to have is the probability the probability of being positive given that I'm sick, right? Or the probability that I'm positive given that I'm healthy. Okay? This is kind of the natural sequence. This is the probability of being sick. It's what we call prior. It's what happens first, right? And you can even like complete the rest of the tree, right? So this is the probability of negative giving S, and this is the probability of negative given H. Okay. So it's kind of natural to have the conditional. But what Bayes' theorem does is it reverses. It asks you the probability of being sick, for example, given that you're positive. So just pause a little bit and observe. It's the other way around of this one. It's flipped, right? Meaning that I don't know if I'm sick or not. I had the positive happening. It happened first. Not exactly happened first, but you have that information first. You have the information of your test first. Okay? And it's not natural by looking to a tree to have this probability here because it's flipped. It's not in the tree. So you have to calculate it. And that's Bayes' formula, Bayes' theorem. So how do we calculate this? How we derive Bayes? Well, we think about this. There are two ways that you could have a positive test. You could have landed on positive by being sick, right? Like this first branch here, this upper branch. Or you could have landed on positive by being healthy. Okay? Because there is a possibility that your test is wrong. It's just giving you a positive, but you're a false positive. Okay? So this flipped conditional is calculated like this. It's a ratio of the number of things that leads me to within all the possibilities that lands me on a positive. So in the denominator is all the possibilities that lands me on a positive. So the upper branch, the yellow branch, leads me to a positive, and it's given by this. And the blue branch, okay, that is this. So again, the yellow branch, it's, if you remember, when you want the branch, when you want the path, you multiply the branches. So the yellow path is this one. It's P of S times P of P given S. And the blue branch is this one. Right? It's P of H times P of P given H. And what is the numerator of the Bayes theorem? Well, it's what interests me. Well, if the question is if I'm sick, like if I have a positive, what's the probability of being sick? Well, that's the yellow branch, right? So the yellow branch, this path is of my interest. Oops. So this is the yellow path. So to derive Bayes' formula, this is the yellow. It's simple as that. Just look at the branches. How are you landing on the positive? Well, within all the possibilities, yellow and blue, I want the one that is yellow. So I will take the yellow in the numerator over all the possibilities that leads me to positive. Okay? So this is the Bayes formula. You can kind of derive it on the go, or you can memorize it. It's up to you. We're going to derive it in an exercise. Yeah.
See, you know what's weird to me is that, like, if both of them are yellow, why don't they cancel each other out and then just leave the blue answer?
Yeah, because so you cannot cancel because this is a sum in the denominator. So let's I'll give you an example. Let's say that you have 2 in the numerator and then you have 2 plus 5 in the denominator, right? So you cannot do this. If it were a multiplication, then you could. But because it's a sum, you can't. So just don't cancel it out. Okay? Now, Bayes' formula can ask you about the blue branch as well. Like, what's the probability of that, given that you're positive, you're healthy? You could do the same thing. You have both ways, right? So it's just the same thing. But now, what you're going to do is you're going to put the, oh, sorry, this is black, look. You're going to put the blue branch in the numerator, which is your, like it's your path that you want. You're blending into positive, given that you're healthy, divided by the paths that lead you to positive. So the numerator won't change, right? The denominator won't change. And, I mean, you have to just do Bayes and figure out which branch is of your interest. Okay. So this is the Bayes formula. Now let's work on the exercise and let's derive Bayes on the exercise. Let's solve the exercise with Bayes. So you can look to the formula and just substitute the values, but I would suggest doing it like trying to reason the tree. So Jen cooks beef for her lasagna 90% of the time and cooks chicken the remaining 10% of the time. So Jane is very nerdy. She keeps tracks of her lasagnas, and 90% of the time she cooks beef, 10% of the time she cooks chicken. When she makes beef, there's a 40% chance her daughter Caroline will completely finish her plate. And if Jane cooks with chicken, there's a 20% chance that Caroline will not finish her plate. This evening, after dinner, Jen noticed Caroline completely finished her plate. What is the probability that Jane cooked chicken for her lasagna? Okay. So we're reading this exercise. And first of all, when you see these answers in the multiple choices here, it's a multiplication on the numerator and a sum of multiplications in the denominator. This will give you a hint that this is Bayes' theorem. Because in the numerator you have one path, and the denominator you have the sum of two paths. Okay? But let's say that you don't have this hint, like it's an open question. How would you know that you use Bayes' formula? Well, think about this. You are given a conditional probability, meaning that if it's beef, Caroline will finish or not her plate. If it's chicken, Caroline will finish or not her plate. So this is the probability of finishing given beef, probability of finishing given chicken, right? Now look at the question. What's the probability that, well, actually Caroline finished her plate? What's the probability of being chicken? So the answer is reversed. It's kind of, well, she finished, but where did she go? Where did she came to the finish? Through beef or through chicken? Can you calculate the probability of being chicken? So when you're reading that and it's reversing the conditional, this is Bayes' theorem. So let's solve it by constructing the tree. First of all, we can do beef or we can do chicken. And after mommy did beef or chicken, the kid, Caroline, will finish or not finish the plate. Finish or not finish the plate. Okay? Now let's populate the tree. Well, beef is 90% of the time. So, and chicken is 10% of the time. Makes sense. Okay, everything is good. It sums up to 1. Now, if it's beef, there's a 40% chance that Caroline will finish. So if it's beef, here's 40%. What else? If it's chicken, that's a 20% chance that Caroline won't finish. So if it's chicken, she won't finish with 20% chance. Okay, so this is all the information given to me. Here's the thing. What is left to this branch here? If the upper one is 0.4. 0.6, right? Because it has to sum up to 1. What about this one? Well, it has to be 0.8, okay? So you have the complete tree. And when you ask what's the probability of, given that Caroline finished the plate, this came from chicken. If you look at the tree, you won't find this probability directly. Right? Because all of the probabilities here are, here, for example, is the probability of F given beef. And here is the probability that you finished given chicken. It's the sequence. Chicken and beef come first. But look at here. I want to reverse the question. I want the probability that, given that I saw that Caroline finished her plate, what's the probability that have been chicken? Okay? So the question is this. Caroline can finish the plate by 2 different paths. It could have been beef and she finished the plate, right? And it could have been chicken and she finished the plate. Okay? So when I'm reversing, when I'm using Bayes, again, I don't need to, you can go and substitute in the formula. Like call S chicken, beef, call H chicken, call P F, and call N not F, right? F complement. And then just substitute in the formula. But let's think about this. How many ways do I have to land in finishing the plate? Well, 2. So in the denominator, I have 2 branches. And they are given for the yellow branch is it's 0.9 times 0.4. And she can also land in a positive, in finishing her plate by doing the blue path. So that's 0.1 times 0.8. Okay? So amongst all the ways she could land in finishing her plate, she could have come through beef, she could have come through chicken. But the question is, what's the chance of being through chicken? That's what I'm asking. Well, through chicken is just one path. It's just the blue path that interests me. So it's 0.1 times 0.8. So this is the blue path. And I did Bayes' formula, Bayes' theorem, without the equation, just by deriving. And the answer is B, right? So you can see that the answer here is B. Again, if you see a path, a multiplication divided by the sum of two paths, the sum of two multiplications, it's a hint that you should use Bayes. Okay? Questions about this last exercise? We're good? All right, so we're just left with repeated trials for Thursday with multiple outcomes and two outcomes. And then we're done with probability. Thank you so much.